So in this video, we take up preparation of aryl halides. Aryl halides, that is aromatic halides. They can be prepared from two types of compounds. They can be prepared from aromatic primary amines. Number two, they can be prepared from aromatic hydrocarbons. First, we take up preparation of aryl halides from aromatic primary amines. Now, for this, you need to understand what is the meaning of aromatic primary amine. This is a primary amine. Although NH2 group is attached to a secondary carbon atom, but this is a primary amine. NH2 group is attached to a tertiary carbon atom, but amine is still primary amine. NH2 group is attached to a primary carbon atom. Amine is primary amine. So remember, whether NH2 group is attached to a primary or secondary or tertiary carbon atom, if the group is NH2, it's a primary amine. If that is the case, then what is a secondary or tertiary amine? Secondary amine is that in which nitrogen is bonded to one hydrogen atom and there are two similar or different alkyl chains. It means in secondary amine, group is NH. In tertiary amine, group is N. This N is attached to maybe same or different alkyl chains. So primary amine group should be NH2. Now coming to aromatic primary amine. In this compound, aromatic ring is present. Primary amino group NH2 is present, but this is still not an aromatic primary amine. Remember, aromatic primary amines are those in which NH2 group is directly bonded to aromatic ring, directly bonded to, let us say, benzene ring. It means this compound is an example of aromatic primary amine, and it's a very important aromatic amine. This is aniline. Aniline is the common name. IUPAC is benzeneamine. This we want to convert into aryl halide. It means we want to replace NH2 group by halogen. But there's no direct method to replace NH2 group by halogen. Rather, we'll have to first convert aromatic primary amine into an intermediate compound, which is called a diazonium salt. And this diazonium salt is then converted into aryl halide. And conversion of aromatic primary amine into diazonium salt is called diazotization. Diazotization. For diazotization, nitrous acid, HNO2, is required. It means this is reacted with HNO2. Again, HNO2 is an unstable compound. This is prepared in situ. For in situ preparation of HNO2, we use NaNO2, that is sodium nitrite, and HCl, which should be concentrated and taken in excess. So in the reaction flask, we take NaNO2, we take concentrated HCl, which should be in excess, plus aromatic primary amine. These two will react together and lead to the formation of HNO2. HNO2 will attack aromatic primary amine and will lead to the formation of diazonium salt. That diazonium salt is then reacted with some other reagents, and ultimately we get aryl halide. In this process of formation of diazonium salt, temperature should be low. It should be 0 to 5 degrees centigrade. Why low temperature? That I'll tell you. So, for formation of diazonium salt, temperature should be 0 to 5 degrees centigrade. Why low temperature? That I'll tell you. So, why low temperature? That I'll tell you. So, First of all, NaNO2 reacts with HCl, concentrated excess, leads to formation of HNO2, that is nitrous acid, and NaCl. HNO2 will attack aromatic primary amine taken in the same reaction flask. HCl was taken in excess, will be used in the second reaction as well. Low temperature is in fact required for the second step of the process, leads to formation of this is diazonium salt. Low temperature is required because diazonium salts are unstable and explosive compounds. They are highly unstable if the temperature is slightly high. Therefore, they are prepared at low temperature so that they do not explode, they do not undergo decomposition. Now I'll tell you about the structure of diazonium salt. This part in the circle is called diazonium group. You can see there are three parts in this structure, and three parts will have three words in the name of this product: benzene diazonium chloride. So the name of this diazonium salt is benzene diazonium chloride. Now this diazonium salt is converted into aryl halide, for which I'm giving you four different reactions. Diazonium is reacted with, X should be chlorine or bromine, is reacted with HCl or HBr in the presence of cuprous halide, Cu2X2, that is Cu2Br2 or Cu2Cl2, leads to formation of aryl halide, nitrogen, and HCl. This method is called Sand-Mayer's reaction. Second method is a slight change. In place of cuprous halide, we use copper powder. Rest everything is same. So this is HX in the presence of copper powder. Halogen is again chlorine or bromine. This is called Gattermann's reaction. No change in products. Products will be same. Third is reaction with aqueous Ki or aqueous sodium iodide. This is not a name reaction, and this will lead to the formation of iodo product. In all these reactions, four reactions, nitrogen will be one of the products. Last method. Reaction with HbF4. HbF4 is fluoroboric acid. This is ionic compound. These two will react and lead to a double displacement reaction. H plus and Cl minus will give HCl. So HCl is one of the products which I'm not using in the subsequent reaction, therefore written minus HCl below the arrow. Chloride will be replaced by BF4 minus. This is also a diazonium salt. Name. First two words will remain the same because this has not changed. Third word will change. Name of this product is benzene diazonium tetrafluoroborate. Benzene diazonium tetrafluoroborate. On heating, this undergoes decomposition and gives fluoro compound. Fluorobenzene plus nitrogen plus BF3. Name of this method, both the steps combined together, name of this method is BALZSCHIEMANN. This is called Paul-Szyman's reaction. So these are four methods to convert diazonium salt into corresponding aryl halide. Now, second category of reactants to convert to prepare aryl halides is from aromatic hydrocarbons. Now, if we consider benzene, it's aromatic hydrocarbon, or any alkyl chain attached to benzene ring, that is also aromatic hydrocarbon. Let us say there is methyl group attached. When we react any, these are called, in general, they are called arenes, ARENES. So when aromatic hydrocarbons are reacted with halogen, halogen should be chlorine or bromine. Why not fluorine or iodine? Reason will be same as I told you earlier. With fluorine, reaction is highly viscous and uncontrollable. With iodine, reaction is slow, and HI form will lead to the reverse reaction, which I told you earlier. Same details are applicable here as well. Anyways, so when aromatic hydrocarbon is reacted with chlorine or bromine in the presence of sunlight, then reaction will take place in the side chain. If the reaction is carried out in the presence of catalyst and cold and dark, no sunlight, cold and dark and catalyst, then the reaction will take place on the aromatic ring. So where do we want to attach halogen? Depending on that, reaction conditions will be different, right? So we'll divide this preparation in three parts. So first part is, if we want halogenation on the aromatic ring, then aromatic hydrocarbon is reacted with halogen in the presence of catalyst, and conditions should be cold and dark. Benzene plus chlorine or bromine. Catalyst may be FeX3 or AlX3 or iron. If it is chlorine, it should be FeCl3, AlCl3. If it is bromine, it should be FeBr3 or AlBr3. Cold and dark. Reaction will take place on the aromatic ring. If halogen is taken in excess, then this product will further react under similar conditions. If halogen is taken in excess, then the product halobenzene formed further reacts with halogen, same reaction conditions, and one more halogen will be introduced. Will get a mixture of ortho and para dihalobenzenes. In 11th standard, you studied about directive influence of groups. Halogen attached to the benzene ring is electron releasing and ortho para directing group. This is the reason we get a mixture of ortho and para products. Similarly, if an alkyl chain is attached to the aromatic ring, alkyl chain is also ortho para directing due to hyperconjugation. This came in your class 11 syllabus. Alkyl group attached to the benzene ring is also ortho para directing in nature. Therefore, if we try to carry out halogenation of any alkyl benzene, let us say toluene, under similar conditions, we get a mixture of ortho and para halo alkyl benzenes. Alkyl will not change. Alkyl will remain the same. We get a mixture of ortho and para halo products. So in general, remember halogen and any alkyl chain attached to the benzene ring are electron releasing and ortho para directing. Therefore, their further halogenation will lead to formation of a mixture of ortho and para products. Out of ortho and para products, para is always major product because there is steric hindrance in ortho product. Steric hindrance, because these two groups are close to each other, they will hinder each other. Therefore, para product is always the major product. So this is halogenation on the aromatic ring. Now coming to second part, if you want halogenation in the side chain, methyl is the side chain, then the reaction has to be carried out in the presence of sunlight. Sunlight. If halogen is taken in excess, then this will further react under similar conditions. Benzyl halide will change into benzyl dihalide. If more halogen is taken, this will further react and last hydrogen will also be replaced by halogen and we get a trihalo product. But this reaction can be stopped at any stage. If you want to stop the reaction at this stage, we'll use aromatic hydrocarbon and halogen in 1:1 molar ratio. If we want to stop the reaction at dihalo stage, then we will have to use aromatic hydrocarbon and halogen in 1:2 molar ratio, right? Similarly, for the final product, we have to use halogen in excess. One thing more, if the side chain has more than one carbon atom, then where will the halogen be attached? If the side chain has more than one carbon atom, then benzylic halide will be formed. It means hydrogen at benzylic carbon atom will be replaced by halogen atom because benzylic halides are more stable. This is benzylic carbon. Hydrogen from benzylic carbon will be replaced by halogen atom. So product formed will be this product, right? I already told you why do we not use fluorine, why do we not use iodine. The reasons are same as in halogenation of alkanes. Now coming to the last part, C part for preparing halides from aromatic hydrocarbons is that when benzene is reacted with chlorine or bromine in the presence of ultraviolet light, then substitution reaction does not take place. Rather, addition reaction takes place at all the 6 corner atoms, corner of benzene ring. Benzene reacts with chlorine or bromine, UV light, addition reaction takes place. Now the product is not aromatic product. There's no ring at the center. We get halogen at every corner atom. This product is called, if it is chlorine, product is benzene hexachloride, BHC. BHC is given many common names, BHC, benzene hexachloride, lindane, gemexane. This is also called 666 is another common name of this compound. Why this funny common name? Because this product has 6 carbon, 6 hydrogen, and 6 chlorine atoms. This is also called 666. IUPAC name of this product, if it is chlorine, IUPAC is 1, 2, 3, 4, 5, 6 hexachlorocyclohexane. This is cyclohexane ring now. Similarly, if we use bromine, then the product formed is BHB, benzene hexabromide. So with that, we finish methods of preparation of alkyl halides as well as aryl halides. Next time, we'll take up physical properties of halides.